Good day viewers. In this episode, we are going to look at quantum vacuum probabilities. I will explain what this means a bit later, but for now, we will look at the standard normal distribution curve. We will do this because we are going to use it as a template for studying quantum vacuum probabilities. The standard normal distribution curve denotes what's called a probability density function. The standard normal distribution has a mean value of 0, and a standard deviation of 1. There's a lot of information available on the internet about the standard normal distribution curve, so I will leave that up to you to explore. What's important to understand about statistics and probabilities is that, if whatever parameter you are considering occurs in large enough populations, then all statistical distributions will eventually converge to a normal distribution. There's a mathematical proof associated with this statement, but it is outside the scope of this presentation, so just take my word for it. If you are really interested in the mathematical proof, you can find it on the internet. It is textbook stuff. What is relevant to us here and now is that we are dealing with photons and gravitons when we talk about the quantum vacuum. These particles occur in such large numbers that the only statistical distribution we can consider which is reflective of natural causes is the normal distribution curve. The reason we are using the standard normal distribution as a template is because it is convenient. Moreover, it is common practice to reach for such a curve, precisely because of its convenience. So, what we are doing here is implementing common practice. What this graph is communicating is that a 68.2% probability exists that the target parameter, whatever it may be, will lie within one standard deviation of the mean value if we randomly selected an artifact from an infinite population. Moreover, there is a 40% likelihood of us randomly selecting an artifact at the mean value. Of course, it should be understood that the total area underneath the curve when the number of standard deviations tends to infinity adds up to 100% probability. In other words, the probability of our random sample being described somewhere underneath the curve is 100%. Anyway, that's all well and good, but how can we use this as a template for quantum vacuum probabilities? Let's have a look. The first form of quantum vacuum probabilities we will consider is the quantum vacuum absorption spectrum. This refers to the proportion of gravitons radiated by matter, which are being absorbed by the quantum vacuum in a gravitational field. Regular viewers of this channel should already be aware that we consider all matter to radiate a vast spectrum of gravitons. This graviton radiation is an energy source, and the quantum vacuum is the energy sink. Or in terms of general relativity, the energy sink is the space-time manifold surrounding matter. In other words, we insist that Einstein's space-time manifold is being continually fed energy in order to curve space-time. This differs from general relativity, which considers the so-called curvature to be permanent if no changes occur to the system as a whole. Needless to say, general relativity is questionable in our opinion because it does not include quantum mechanics or the quantum vacuum in any way, shape or form. Okay, so what is a graviton according to the electrogravimagnetic construct? Well, to cut a long story short, a graviton is an entangled conjugate photon pair. Or in other words, a graviton is a positive wave-function photon, coupled to its mirror image, that is, a negative wave-function photon. In relation to the graph appearing on screen, the negative wave-function photons occupy the left-hand side of the curve, and the positive wave-function photons occupy the right-hand side, as indicated by the modes and frequencies labeling. This kind of symmetry is a fundamental requirement of quantum electrodynamics. If it wasn't included, then the quantum vacuum would be asymmetric at a specific point, and an inexplicable net radiation effect would seemingly appear from nowhere. So, the stated symmetry is a basic requirement, there is no way around it. Moreover, this wave-function symmetry is also a requirement of the Fourier series decomposition of a constant function, we derived in episodes 1 to 4 on this channel. Please refer to these episodes for more information. You can see that we have replaced the standard deviations of the x-axis with harmonic modes and frequencies. The graph shows that approximately 63.66% of all gravitons being radiated from an object occur at the fundamental harmonic frequency, that is, between n equals -1 and n equals 1. Hence, approximately 31.8% of the coupled photons will possess negative modes, whilst the same proportion will possess positive modes. Similarly, at the third harmonic, a total of approximately 21.22% of gravitons will be absorbed by the quantum vacuum, so on and so forth, as indicated on the graph. Of course, the sum of everything beneath the curve demonstrates that 100% of gravitons are absorbed by the quantum vacuum at every point in any space-time manifold, that is, up to the quantum vacuum cut-off mode and frequency. I should emphasize at this moment that the same distribution curve applies to every point in a polarized quantum vacuum field. Or in other words, it applies to every point in a gravitational field, in precisely the same way, with precisely the same graviton population density function. Okay, now that we have looked at how the quantum vacuum is absorbing energy, let's have a look at the quantum vacuum emission spectrum. When we refer to the quantum vacuum emission spectrum, what do we mean? Well, within the electrogravimagnetic construct, we are referring to the Casimir effect, which we claim is driving accelerated cosmological expansion. The Casimir effect involves the creational annihilation process associated with virtual particle pairs, that is, with the creation annihilation of positive and negative wave-function pairs. These pairs pop into and out of existence, almost instantaneously. Once again, they must occur in pairs, otherwise mysterious radiation would seem to be appearing from nowhere. What this all means is that the quantum vacuum emission spectrum is identical to the quantum vacuum absorption spectrum. However, what differs between them are the population of photon pairs associated with each spectra. More gravitons are being absorbed by the quantum vacuum than conjugate photon pairs being emitted from the quantum vacuum. Hence overall, a net flow of energy transitions into the quantum vacuum. As mentioned previously, matter is an energy source, and the quantum vacuum is the energy sink. This means that all matter will eventually evaporate into the quantum vacuum, over cosmological time. This of course, gives rise to a cyclic model of cosmology, and provides the Roger-Penrose model of conformal cyclic cosmology, the missing and necessary matter evaporation mechanism it requires. What this all means is that a certain number of photons are entering the quantum vacuum, let's call them X, and a certain number of photons are leaving, let's call them Y. However, X does not equal Y. In fact, in previous episodes on this channel, we have derived a result of X equals 2Y, as appears on screen. This means that on average, for every 2 photons entering the quantum vacuum over cosmological time, 1 photon exits. This process powers accelerated cosmological expansion, via the Casimir effect. We claim that this is the root cause of the dark energy phenomena. In other words, the dark energy phenomenon is simply the Casimir effect, acting on a cosmological scale, over cosmological time. At each instant when a conjugate photon pair is created, then annihilated, via the Casimir effect, the universe responds by expanding a little bit to accommodate the new wave functions, which have fleetingly existed and subsequently collapsed. Because this process is continuous, the universe is always expanding and never has a chance to contract. A couple of obvious questions arise from our description, that is, when a conjugate wave-function pair is created, where does the energy come from? Similarly, when a conjugate wave-function pair collapses, where is the energy stored? We propose that the ground state of the quantum vacuum, termed the zero-point field, acts as a pressure release valve for a layer of inaccessible reality beneath it, termed the dark reservoir of quantum potential energy. Hence, matter evaporates gravitons, and these gravitons are stored in the dark reservoir of quantum potential energy. The dark reservoir of quantum potential energy is a fourth spatial dimension which in turn, feeds the zero-point field with quantum potential energy. Consequently, the zero-point field feeds the Casimir effect and accelerated cosmological expansion. Therefore, the system is a closed loop, and the law of conservation of energy applies and is obeyed. In other words, baryonic matter radiates populations of gravitons which are absorbed by the dark reservoir of quantum potential energy, via the zero-point field interface. General relativity interprets this absorption as space-time curvature. Thus, the mechanism we have described is isomorphic to general relativity. However, as one might expect, the store of gravitons within matter is finite. This means that all matter possesses a minimum gravitational lifetime. Please refer to episodes 6 and 19 for more information. The important takeaways from this illustration are: 1. All matter acts as an energy source. 2. All matter evaporates via graviton radiation. 3. The gravitons radiated by matter are absorbed by the dark reservoir of quantum potential energy, via the zero-point field interface. This means that the dark reservoir of quantum potential energy acts as an energy sink. 4. The zero-point field interface is a bidirectional information layer, allowing gravitons to enter the dark reservoir of quantum potential energy, but also acting as a pressure release valve which we perceive as the Casimir effect. To ensure that the dark reservoir of quantum potential energy inflates very gradually, the zero-point field releases energy back into the physical universe to drive the experimentally observed accelerated cosmological expansion. Let's now summarize what we have learned. The lessons learned in this episode are quite straightforward. 1. The quantum vacuum absorption and emission spectra possess identical profiles, that is, they are both normally distributed. 2. For every 2 photons entering the dark reservoir of quantum potential energy, 1 photon exits via the zero-point field. 3. The zero-point field acts as a pressure release valve, via the Casimir effect, which drives accelerated cosmological expansion. 4. The probability of at least 1 virtual photon popping into existence at each harmonic is equal to the proportion of gravitons entering the dark reservoir of quantum potential energy as matter evaporates. Please note, in our last statement, we specified the probability of 1 virtual photon popping into existence at each harmonic, rather than a coupled conjugate photon pair. This was an intentional specification, in order to hedge our bets against the possibility of singular photons being able to undergo the creation, then annihilation process. In other words, quantum electrodynamics requires that a coupled conjugate photon pair be created, then annihilated, but it may be possible that this process does have some currently unknown exceptions. Therefore, to ensure the timelessness of this episode, we have included a statement addressing the possibility of singular photons.